Okay, now here's think of this as a string. It's a piece of tubing. But if you think of this as a string, I can oscillate this string like so. Okay? And that oscillation has very little movement at this side. I'm not moving my finger much at all. The middle of the string, we'll call it a string, is moving a lot more than my finger is. And I can even abbreviate the motion of my finger even more if I increase the tension and the frequency. Okay? So this end is essentially fixed. It's oscillating very slightly about an equilibrium point. This end is fixed. Now, that motion is well described by the motion of, well, by the wave that we've constructed, the orange wave, let's say. It's here at equilibrium, and then it gets a peak on one side, goes back to equilibrium, peaks on the other side. Hopefully you can see how that mimics what we just saw with the so-called string. And the ends are nodes. The ends have no displacement, and we call a point that has no displacement on a wave a node. And in the middle, we have an antinode, a point where you have maximum displacement. Now, you don't have that maximum displacement at every instant, but unlike this point on the string that doesn't move, this point moves to an extreme point, back to equilibrium, and to an extreme point on the opposite side, and then the whole thing will happen again. We'll move back to equilibrium, etc., etc. So this figure illustrates how that wave can form between 2 points. Okay? Now there are other waves that can form between 2 points, but what I'm going to say is this picture can be used to represent the development of a standing wave in a string of any length with a wave of any wavelength, as we'll see in a minute. And the statement I've written here is, if the string length is L and it spans from here to here, if this represents the length of the string, then 1/2 lambda equals L, because, of course, these lines are a quarter of a wavelength apart. The whole wavelength runs from here to here. What we have between these two lines is only 2 of the quarter wavelengths, half a wavelength. So half the wavelength equals L, and then it's obvious then that lambda would be equal to 2L. The wavelength that you would get would be double the length of the string. Now, we haven't specified a scale on this picture. I just assumed one. I assumed that this is a string length. And here's our model of the development of the wave. And we can think of these waves as just an infinite train of these waves coming along this way and this way, causing this behavior to occur, the behavior of the orange graph, the equilibrium, antinode, equilibrium, antinode behavior. I can make other assumptions. I could assume that this from here to here is the length of the string. Okay, so if this is a string length L, then how many quarter wavelengths is that? What is the wavelength lambda? Well, if this is your length L, then it's pretty clear that this is a full wavelength, 1, 2, 3, 4 quarter wavelengths, and we have lambda equal to L in this case. Now, of course, we can't have both this and this on the same graph at the same time, so we kind of say, okay, well, if that was it, we'd have this. Now, if this represents the length of the string, then we have this wave. And what does this wave do? Well, it's equilibrium, but then it forms a peak here and a valley here. Then it goes back to equilibrium. Then it forms a valley where the peak was and a peak where the valley was. So you have the two ends of the wave. They're equilibrium. One of them comes out this way while the other goes the other way. And then they come back to equilibrium and go like this. So the wave is kind of moving like this. The wave motion looks a little bit like that. And that's kind of the way it feels when you set it up in a string or a rope. And we see that, again, we have a node at this end and this end, so that's something that could actually happen with a string of length L. Now, if a string of length L was to span, let's say, from here to here, then you would have what? You would have 1, 2, 3, 4, 5, 6 quarter wavelengths. 6 quarters is 3 halves. So 6 quarter time of the wavelength, which is 3 halves of the wavelength, is equal to L, the length of the string. So that lambda is 2/3 L. And we could model any other. We could run all the way from, let's say, here, all the way over to here. What would that be? That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14 quarter wavelengths. So you'd have 14 quarters of lambda equal to L, and that'd be 7 halves, so lambda would be 2/7 of L. You get a whole sequence of wavelengths that can occur in a string of length L.